Have you ever seen a headline about some new miracle drug or a scary new health risk and just wondered, how did they actually know that? Well, behind almost every single one of those stories is this hidden engine, this powerhouse science called biostatistics. Today, we're going to pull back the curtain and follow the exact journey a health discovery takes, all the way from a simple question to a life-changing answer. Here's our roadmap. We're going to see why we need this stuff in the first place, how researchers hunt for clues in the form of data, then how they organize those clues to make sense of it all. After that, the really cool part, figuring out what's real versus what's just random chance. And finally, we'll see how they connect all the dots to reach a conclusion that can literally change all of our lives. All right, let's dive in. Every single medical breakthrough, every piece of health advice you've ever gotten, it all starts in the exact same place, with a simple but really important question. Think about it for a second. Let's say someone takes a new pill for a fever, and their fever goes down. Great, but was it the medicine, or was their body just going to fight it off anyway? That's the puzzle, right? Separating a real effect from pure random luck. And to do that, you need a very special toolkit. And that toolkit is our hero for today, biostatistics. All it really is the science of using numbers and data to figure out how health and medicine work. It gives us the rules and the methods to go from a gut feeling, from an "I think this works," to being able to say with confidence, we have the proof that this works. So, we've got our big question. Now, we need evidence. And in science, evidence means data. But you can't just, grab a bunch of numbers from thin air. This hunt for clues has to be done the right way. First things first, researchers defined what's called the population. Now, that's the entire group of people they want to know something about. It could be, say, all adults with high blood pressure, or every person in a country. The problem is, you can't possibly study everyone. It's just way too big. So what's the solution? You take a sample. A sample is just a smaller, more manageable slice of that giant population. But here is the absolute key. For the results to mean anything at all, that small group has to look like a mini, perfect replica of the whole group. The best way to think about it is like a big pot of soup. The entire pot is your population. Now, you don't need to eat the whole thing to know if you added enough salt, right? You just need one well-stirred spoonful. That spoonful is your sample. If it's a good spoonful, it tells you everything you need to know about the entire pot. That's why how you pick that sample is so incredibly important. So, how do you get that perfect spoonful? Well, you've got a couple of options. You can collect brand new data yourself through things like surveys. That's called primary data. Or you can use info that's already out there, like hospital records. That's secondary data. Now, the best way to choose people is with probability sampling. That's where everyone in the whole group has a fair shot of being picked, kind of like drawing names from a hat. Sometimes, though, that's not possible. So researchers might use non-probability sampling, which is based more on who's easy to reach. The main thing to remember is that the method you use here can totally change how much you can trust the results at the end. Okay, the hunt is over. We've collected our data. The thing is, right now, it's probably just a giant, messy spreadsheet full of numbers. It doesn't tell us anything yet. The next job is to bring some order to this chaos and make those numbers actually tell a story. Sometimes the simplest tools are the best. A basic table can be incredibly powerful. Just look at this one, showing the top causes of death around the world. It's got a clear title, neat rows and columns, and bam, a huge, complicated set of data becomes easy to understand. Your eye goes right to the top of the list. That's what good organization does. Another great way to tell a story is with a donut chart like this one. It's perfect for showing how a whole is divided up. In just one glance, your brain immediately gets it. A massive piece of the global tuberculosis problem is concentrated in just a handful of countries. It's visual, it's fast, and it makes a huge impact. And if you want to share data with the general public, you can't beat a pictogram. It uses simple little pictures to represent numbers. Here, each little person represents 1,000 malaria cases. You don't have to be a math whiz to look at this and instantly see the trend over the years. It's just a brilliant, intuitive way to get a point across. So we've organized our clues, and we're starting to see some patterns emerge. But this brings us to the most critical step of the entire journey. How do we know if the pattern we're seeing is a real discovery, a true signal, or if it's just random noise, a total coincidence? You have definitely seen this shape before. It's the famous bell curve, and it is a cornerstone of statistics. It pops up everywhere in the natural world, from people's height to their blood pressure. Basically, it shows that most of the time, things cluster around the average in the middle. And extreme results, way out on the edges, are pretty rare. It's like a map of what's normal and what's not. So, how do we read this map? Well, we use a concept called standard deviation to measure how spread out everything is. You can think of it like big steps away from the average in the middle. And here's the most important rule of thumb. About 95% of all the data will fall within 2 of those steps of the average. So if you get a result that falls outside that 95% zone, well, that's considered pretty unusual. That's an outlier. It's the kind of result that makes a scientist lean in and go, what's going on here?
This leads us to the final test. How do we make the call? Is our result a real finding or just a random fluke from that rare 5% zone? The answer is something called the p-value. You can think of it as a fluke detector. It calculates the exact probability that you'd see the results you saw if it was all just random luck. And if that probability, that p-value, is really, really small, typically less than 5%, scientists declare the result statistically significant. It means it's super unlikely to be a fluke, and they probably found something real.
We've made it to the final stage. We've collected our data, we've organized it, we've tested it to make sure it's not just a fluke. Now it's time to connect all the dots and deliver the final verdict. One of the big things researchers look for at this stage are relationships, or what's called correlation. Take a look at this scatter diagram. Each dot represents a person, plotting 2 different measurements. See how the dots aren't just a random cloud? They seem to form a rough line going up. That pattern is a huge visual clue that these 2 things are connected. As one goes up, the other tends to go up too. But, and I cannot say this loudly enough, this is maybe the most important rule in statistics. Just because 2 things are connected does not mean one causes the other. The classic example is that ice cream sales and shark attacks are correlated. They both go up in the summer, but eating ice cream doesn't cause a shark attack. The real cause is the hot weather that makes people swim and eat ice cream. Always, always remember that difference. To take it a step further than just seeing a connection, scientists use an even more powerful tool called regression analysis. This doesn't just show a relationship, it actually helps you predict things. It lets you ask questions like, okay, based on our data, if we know a person's age, can we predict what their blood pressure is likely to be? It turns a simple pattern into a predictive forecast. And there you have it, the whole journey, from start to finish. We started with a simple question, we went out and gathered our sample, we organized the data into charts and tables, we used the bell curve and p-values to make sure our findings were real, and then we used correlation and regression to connect the dots. That whole structured process, that is the power of biostatistics. So the next time you read a health headline, you'll know about the incredible hidden journey that happened behind the scenes. This whole process, questioning, sampling, analyzing, and interpreting, is happening right now in labs all over the world, powering the next big medical breakthrough. It just makes you wonder, what massive health mystery are they going to solve next?